Hi, my name is David, and I'm here representing Rebalance Energy, a company focused on changing the way the world stores its energy. Since it's the last day of the conference, right after lunch, and we're all a bit hungover and suffering from conference fatigue, I'm going to try to spice things up a little bit. My parents were teachers and liked to use the Socratic method on me growing up, so I'm going to take this opportunity to try that all out on you. So, first question, which of these has more stored energy? 1,000 milliliters of water or a standard battery like this one from my laptop? I'll give you 20 minutes or so to think it over as we go through the presentation. So today I'm presenting modeling the benefits of distributed hydroelectric storage. And the images I have here are from the Yuba Bear hydroelectric relicensing project. I was working for DTA at the time that this project was going on, which then got acquired by HDR. And we built a combined water and power model for this project. It was led by my old friend, Rick Jones, and I got to travel down to Sacramento and work on the project. This is an amazing project in that it's 270 megawatts total capacity, but it is in 40 interconnected reservoirs with 13 open channel water conveyances and 16 powerhouses within the Yuba Bear and American River watersheds. So you can think of this as a distributed water storage project, but I like to think of it as a distributed energy storage project, with that energy being released by those 16 hydroelectric powerhouses. And that's the core of the rebalance technology that I'm going to talk about towards the end of the presentation. Is we think that distributed hydroelectric energy storage has the potential to beat out any energy storage technology you want to throw out there. All right, so what is a model? Let's go to the web and ask Merriam-Webster. So a whole bunch of definitions come up. All right, is it definition 4, like this 3D printed model of a turbo turbine that I printed out? Or is it, these dueling models heading off into a walk-off? I think probably the most appropriate definition for us is definition 12, which is a system of postulates, data, and inferences presented as a mathematical description of an entity or state of affairs. But that postulates word, it's just the GRE word. I like to use the word assumptions. All right, so keep in mind assumptions. All right, so I've got a few simple models that I've put together and some plots that I'm going to start out with. So this one is it's a historical model of energy storage. So over the last 10,000 years, humanity has progressed from collecting wood and storing it to burn in the winter, up through nuclear submarines that only need to be refueled every 20 years, and sending people into orbit using energy stored in liquid hydrogen. And this is a log plot. So really, we have progressed many orders of magnitude in our ability to store energy. Based on the historical model, what would you, the audience, choose as the energy storage technologies of the future? All right, so what I would choose are the ones that are clearly beating the curve, right? So uranium, plutonium, liquid hydrogen, very high speed, high efficiency flywheels. All right. But society wants renewable energy storage. So let's remove the data for compressed dead plants and animals and that quasi magical uranium stuff. Just look at the stuff that we could define as renewable. Now, what would you pick as the energy storage technology of the future? Again, liquid hydrogen, 120 kilojoules per kilogram energy density. The NASA flywheel program in 2004 achieved 500 kilojoules per kilogram in a high-speed flywheel spinning at 10,000 RPM. So from an engineering perspective, if all I cared about was energy density and sending something to the moon or to Mars, we've got some clear winners here, right? But as we all know, engineers don't run the world, accountants do. So what does the capitalist model for renewable energy look like? Well, here's what the EIA, a division of the US Department of Energy, puts out there on their website. This is from 2017. It's the average cost of new generating assets by class in the United States. So what sort of renewable energy project would you build from looking at this data? I guess I've helped you out here by already circling the two lowest cost renewable sources, and that's wind, and then backing that up with battery storage. But this is a great example of why the data matters. So this is from the US from 2017. And you notice that none of those technologies that won just from a pure engineering perspective are on there. Well, why is that? So let's put that data out there. All right, so now we can get a more complete picture. So why aren't we building nuclear? Well, because it's $10,000 per installed kilowatt. That's what's estimated to be the cost of the Vogtle plant that's being built right now. Flywheels are getting close, but they're still not competitive with chemical batteries. Hydrogen is super expensive. It's very difficult to handle, very difficult to store, extremely volatile. I mean, 2 space shuttles exploded during NASA's shuttle program, right? But what does become more clear is that, yeah, batteries are getting pretty cheap. The big battery that Tesla put in Australia is $630 per installed kilowatt. So on a capacity basis, very competitive. But you know what else is really competitive? Hydro. So I've added 2 examples here of historical projects, because what I think we're seeing in the 2017 data is that most of the low-hanging fruit for hydroelectric projects in the United States have already been built. And based on my experience developing small hydro projects in North America, the projects that are getting built today are really marginally feasible projects. So that $5,000 plus per installed kilowatt is kind of a misleading number. If you include historical data with costs adjusted to 2017 dollars, then I think you can get a good idea of the real range of development costs for a good hydro project. So I have a very high head project here in Switzerland at $950 per installed kilowatt, and a very low head project on the Columbia River, the Wells project, which adjusted from 1967 was built for about $1,400 a kilowatt. All right, so that's what you would build if you're just looking at the cost of capacity. But we're here to talk about energy storage, right? And storage isn't kilowatts, it's kilowatt hours, right? So let's just look at the data. Let's look at the model that I built here. What would you build? Right? Clearly, it's pumped hydroelectric storage. Because it's the only thing that can build cost-effective storage at large scale. That Tesla project, the big battery out of Australia that's getting all the press, yeah, it was cost competitive on a capacity basis. But if you look at the cost per kilowatt hour, it's still over an order of magnitude higher than the best hydroelectric storage projects. All right, so our model that I'm going to propose here is that we should be looking at the life cycle costs of these different energy storage technologies, because it's not just about how much you're going to pay up front, it's about how much it's going to cost to maintain the project, how much your repair is going to cost, and what are the retirement costs at the end of the project's life. Because project-specific details can have a major impact on cost, and frankly, because this data can be hard to get in the public sphere, I'm showing what I consider to be the low and high estimates for the real life cycle costs of each one of these technologies. So what would you choose based on this model, right? I mean, clearly, hydro refurbishment is the low-hanging fruit. These projects have already been built for a relatively low cost. You can refurbish the fleet, upgrade the controls, upgrade the generators to react more quickly. You've got a ton of energy storage already sitting out there. All right, so going back to the all models are wrong, some models are useful. I like to say useful models help make good decisions, good risk-informed decisions. So which one of these models that I've proposed would you say is useful? All right, so I would contend the answer is F. All of these models are useful. It all depends on how you view the risks. So this is an example risk register. This is something that I did a lot when I was doing consulting and due diligence. After you've come up with these costs, these great models, you also have to talk about the risks, the uncertainties, right? So if we look at the historical model, nuclear and hydrogen, yeah, that's great on a kilojoules per kilogram basis, but there's high technology risks, there's high environmental risks, and the cost risks are huge. Just look at what's happening with the new build nuclear projects in the United States right now. If we look at the engineers model for renewable energy, which is flywheels and hydrogen, again, high technology risks. These are technologies that still need to be developed. The environmental risk is low, but again, your cost risk is high, which is often driven by your technology risk, right? Again, the accountants usually get it right. So the model they have for renewable energy capacity and storage, much lower risk almost across the board. But then I think the life cycle cost model is really what minimizes your overall risk portfolio, because it leads you to the conclusion that we should refurbish what we already have, where the environmental impacts have already happened, where the technology is proven, and where the cost risk is really not that big. All right, so you know what they say about assumptions, right? What I say is they're critically important to the accuracy of any numerical model. And any good modeler will tell you that depending on your base assumptions, you can make a model say whatever you want it to. That's why my graduate advisor taught an entire course on finite element modeling where we never even touched a piece of software. We were learning to calculate the finite elements by hand because he liked to say if you don't understand the underlying math, the underlying physics, and the assumptions of a model, it's just an expensive coloring book. And this is coming from a guy that spent his entire career building complex fluid structure interaction models like LS-DYNA, of which he was on the development team for. So as I go through the second half of my presentation, think about the assumptions that you've made in how you model renewable energy storage, and how are these assumptions affecting the accuracy of your results and what you think the most technically and economically feasible technology is that's going to allow us to get to these high levels of renewable energy penetration that everyone's going for. All right, so the central station energy storage model. This is one that's typified by projects like Grand Coulee. The capacity and storage available at Grand Coulee is huge, and it helps to integrate a fleet of nearly 5,000 megawatts of variable wind energy in the BPA balancing area. It also has some of the biggest flywheels in North America at the third powerhouse. They run sync condensed, sometimes more than they generate in a year. So how much do you think it would cost to upgrade the Keys generating plant to allow for near real-time dispatch of that 300 megawatts of reversible pump generating capacity at the plant? And the answer is there for you. Back in 2010, 2011, when I was working on the project, we were estimating about 200 million. So adjusting for inflation, let's say it's 300 million. Let's just throw that number out there. that's still $1,000 per installed kilowatt. That's way below any new project that you could build, right? And the storage cost is less than $9 per kilowatt hour. Remember Tesla's big battery in Australia? That's that's 50 times lower than the storage cost for Tesla's big battery. So this is really the low-hanging fruit for energy storage in North America. Let's refurbish the existing hydroelectric fleet. You will never find better opportunities for large-scale energy storage. All right, but new technologies exist, and new technologies typically require new models. As we've gone through history, I've just listed some examples here. Um, you need a new model when you have a new technology. Sometimes the new model comes first. Um, in the example of field theory was developed, and then very quickly the electric dynamo took advantage of it. But other times you have the technology like the internet, and it was years before people figured out how to monetize it, and we had the e-commerce revolution. But the big takeaway here is that we really haven't had that much sort of disruptive technology in renewable energy since the invention of the photovoltaic cell in 1948. That was the last really big game-changing technology. And a lot of people think that strong AI is going to be that next big disruptive technology. That's what the smart money's saying, right? And personally, I don't want the AI to be making the decision on how we're going to deal with the renewable energy storage problem, because if movies are any indication, we could all end up in a big living battery bank. So that's why I started Rebalance, to help develop new non-AI energy storage technologies. All right, so the new model that's being developed by the battery folks to try to make batteries this disruptive technology for renewable energy storage is distributed energy storage. This is the idea that you're going to have a battery powered car in every garage and smart chargers that can be controlled remotely. And when deployed in coordination with smart meters, their model claims to be able to reduce peak load without substantial investments in the transmission system. Their model would eventually have us all living in solar-powered homes with microgrids using batteries for energy storage. It could, in the end, create a wireless electricity system not unlike the wireless telephone network. And of course, the poster child of this distributed energy storage model is Tesla, who is looking to combine their electric vehicles and power walls with SolarCity's solar shingle technology to one day take us all off the grid. They definitely have a nice website and some of the best promotional videos I've ever seen. A few months ago, I went online and priced out what a Powerwall system would look like for my house in Wenatchee. And it came out to $25,000 in round numbers, including that pesky installation cost that they put in the fine print over there, for 24 hours of storage. That's almost $700 per installed kilowatt. I thought to myself, or per installed kilowatt hour, I thought to myself, I have to be able to do better than that. That's my benchmark. So this is one of the technologies that Rebalance is working on. You can go to the website and see a couple of others. So it's a distributed micro pump storage system. We're calling it PQ. And the concept is that we would install a settling tank between an energy consumer, say a residence, but it could be a commercial business or even a large industrial user, where we would take dirty wastewater and store it. That water could then be pumped up to a high pressure in an air over water accumulator during oversupply hours and used to generate electricity via a high head turbine generator during periods of peak demand, again, shaving that peak load. A 3 kilowatt residential system could easily be installed in the average front. And then our business model is not unlike that of Tesla and SolarCity. Rebalance would be manufacturing, operating, maintaining a network of home scale P-cubed units located behind the electric meter on subscriber's property. Um, for a residential subscriber, we think we could charge about $155 per month, which, by the way, is $10 less than what Solar City wants to charge you for an all-in solar and storage system. And the unit cost for these P-Cube systems, we think we could build and install them for about $7,000 a piece. So considerably less than what Tesla is pricing their power walls at currently. Based on this business model, we think we could generate a profit of about $106 million a year, assuming 100,000 subscribers, on operating costs of $70 million. And we would have a total installed capacity of about 300 megawatts. That's similar to that Keys pump generating plant I showed you previously, with a cost of storage of less than $200 per kilowatt hour. That's 60% less than what Tesla wants to charge me for my new Powerwall. So based on this model, what would you choose as a home scale renewable energy storage system? Would you choose Tesla, or would you choose micro pump storage? And I'll just close with some quotes. The elephant in the room, Elon Musk there. David Thoreau, one of my favorite philosophers and writers of all time. Things do not change, we change. And my feeling is society's changing. They want renewable energy. There's going to have to be storage. And for hydroelectric energy storage to compete, which we all know it can, we're going to have to adapt our model to changes in society and develop different sorts of projects. Albert Einstein, we cannot solve our problems with the same thinking that we used to create them. So, leave you guys with that. Thank you.